This is Kristine Johanning in Lab M05 on Wednesdays from 3 to 6. This is my Lab 1 constant velocity motion. I'm observing rolling duct tape, and the main result shows that based on the fundamental momentum principle, F net equals 0 is an assumption that proves in this model that there is a good prediction of the observed motion. As we go to tracker, you can see the duct tape rolling. It starts to move after the push has already given it the velocity. The first frame set the origin at center of roll. The x-axis is positive in the direction of movement. The bottom of the ball is the average position, and the diameter was used through the calibration stick of 0.1 meters. The time between frames was 0.033 seconds. The total frame is about 2 seconds. I cut the video to stop the motion before the ball fell off the table. The mass of the duct tape is approximately 0.4 pounds, but this will not be utilized in further calculations. The initial position from the analysis of the first frame shows how you can calculate the initial position, and the average velocity is the delta x over the entire clip divided by the total time of the entire clip. We are provided with the initial velocity to use in the model, and delta t was small in comparison to the 2-second elapsed time for the video clip. Now we're showing the code. It is edited to show that from time t equals 0 until t equals 2, we applied Newton's second law, and the velocity prediction and the final velocity includes the second term where F net divided by m times delta t equals 0 only happens when m does not equal 0, delta t does not equal 0, which requires that F net equals 0 to predict the motion. Once again, the mass is not necessary. Here is the visualization of the graph. Since it's only moving a short distance, it doesn't move greatly. At this point, we're going to go to the Excel spreadsheet, and you can see the graph that shows that there is a prediction and the plot and the data from the experiment, and they follow a general trend line. The blue diamonds are from the experiment, and the red line is from the model. Since they are very similar, this implies that there is a good agreement for the model and experiment. What if when you analyze the data in the tracker, you made a choice of origin for your coordinate system? Discuss briefly how your results would change and how they could remain the same if you made a different choice. So I originally had the ball moving right as the positive direction. So if the ball was moving to instead the negative direction was when the ball moved to the right, it would look something like this. You have to go into the code and allow the vectors to be negative for the initial position and velocity, and that will allow the chart to move to the left. Since the graph gets more negative as time advances, we can see that this is accurate. What does it mean? The observations can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? So since we started with a constant velocity, since the picture was not shown until after the initial force was given, we found that by setting F net equal to 0, we had a good fit. This implies that if F net does not equal 0, then the velocity will not be constant. If we go back to the code and remove the negative signs from the previous example, we then would like to go to the force part and change it so that it's not originally 0, where any other value would take place. Then when you run this model, you can see that it moves to the right as the first example did, but it changes either direction or speed, which does not imply that the F net equals 0. Thank you.